Hello, my name is Jordan Street, and I'm from the University of Florida's Electrical and Computer Engineering Department. This presentation on OFDM simulation is done in fulfillment of a class project for wireless communications. We'll start with an introduction to OFDM, followed by a description of a typical OFDM system. The system will be evaluated in MATLAB in the presence of a noisy multipath fading channel. Related work will be discussed and conclusions will be drawn. At the end, I will go through some of the MATLAB scripts used for simulation. So, orthogonal frequency division multiplexing, or OFDM, is a very popular communication technique used in many of today's modern systems. Specifically, it is a multi-carrier wideband digital communication method found in 4G, DSL, Wi-Fi, many other systems as well. OFDM uses a large number of closely spaced orthogonal carriers to transmit data on parallel streams. This allows us to reduce the symbol rate for fixed data rate and bandwidth. The slower symbol rate allows us to insert a guard interval in between each frame, which helps minimize inter-symbol interference. Several advantages to OFDM include a high spectral efficiency, strong interference rejection, and low implementation costs. Disadvantages include a loss in efficiency due to the guard interval, high peak to average power ratio, and a sensitivity to both frequency synchronization and Doppler shift. Displayed here is the baseband block diagram for a typical OFDM system. A binary stream of data is first shifted into parallel blocks. These parallel blocks are then mapped to symbols according to the selected modulation scheme. Examples here include BPSK, QPSK, 16 QAM, etc. The inverse fast Fourier transform is used to move the data to the time domain. Once in the time domain, the signal is shifted from parallel blocks to a serial data stream. A cyclic prefix extension is added to combat inter-symbol interference. Now the OFDM signal is subject to a multipath fading channel, in addition to additive white Gaussian noise. At the receiver end, the cyclic prefix is removed. The data is shifted into parallel blocks for processing. Now the fast Fourier transform is used to shift the data into the frequency domain. And now once in the frequency domain, channel estimation is applied. In our case, least squares estimation is used. The data is then demodulated using the same modulation scheme in the receiver. This is shifted from symbols to bits, and finally these bits are shifted from parallel blocks to a serial binary stream. In order to simulate more realistic conditions, we use the following channel model, which includes additive white Gaussian noise and multipath fading. X of n is the OFDM signal, G of n is the channel impulse response, W of n is noise, and Y of n is the corrupted OFDM signal. To combat the effects of multipath fading, we estimate the channel in the following manner. We first drop the noise term since it's zero mean, and we move the expression to the frequency domain. By propagating a known signal, x of omega, we can use the output y of omega to estimate g of omega. With an estimate of the channel, we can then estimate the original OFDM signal as g omega inverse times y omega. This process is referred to as least squares estimation. The known signal x of omega is referred to as the pilot signal and can either be of block type or comb type. Block type pilots are periodic in time but span the entire frequency range, while comb type pilots are periodic in frequency but span the entire time range. We now simulate the OFDM system in MATLAB, first ignoring multipath fading effects. We use an FFT of size 64 and a cyclic prefix extension of length 16. The bit error rates for various digital modulation schemes in OFDM are examined at different SNR values. We first look at binary phase shift keying. BPSK consists of 2 points on the in-phase axis opposite the quadrature axis and maps one bit to one symbol. For 0 dB SNR, we achieve a bit error rate of 7.6%. By increasing the SNR to 5 dB, we can reduce the BER down to 0.55%. Quadrature phase shift keying expands BPSK by adding 2 additional points along the unit circle. QPSK maps 2 bits to one symbol. For 0 dB SNR, we achieve a bit error rate of 21%. By increasing the SNR to 5 dB, we can reduce the BER down to 5.6%. 8 phase shift keying expands QPSK by doubling the number of points along the unit circle. 8 PSK maps 3 bits to 1 symbol. For 5 dB SNR, we achieve a bit error rate of 19%. By increasing the SNR to 10 dB, we can reduce the BER down to 5%. As we move to higher order modulation schemes, the pattern continues. For a fixed SNR, the higher order modulation has a larger BER. You can see this manifest itself in the transmitted and received images. These next charts demonstrate 16, 32, and 64 quadrature amplitude modulation. As the modulation order increases, the constellation becomes more dense and a higher SNR is needed to preserve the bit error rates. We now consider the effects of multipath fading. These charts demonstrate the effectiveness of channel estimation. Shown here is the received constellation and image for BPSK in a fading channel without channel estimation. We now apply the estimation and improve the BER dramatically. This is repeated for a higher SNR case with the same results. We now examine QPSK in the fading channel. With no estimation, the recovered image is unrecognizable. Although the BER is still relatively high, by applying estimation, we can now recognize the image. This is again repeated for a higher SNR with similar results. The primary related work in OFDM deals with different methods of channel estimation. This presentation dealt exclusively with least squares estimation in the frequency domain. However, there are many other methods in both the time and frequency domain for block and comb type pilots. Least squares is often extended to take advantage of second-order signal statistics. This leads to minimum mean squared error estimation, which, while being more accurate, requires much more computational effort. Throughout this presentation, we've observed that various digital modulation schemes are effective when paired with OFDM. We specifically looked at BPSK, QPSK, 8PSK, 16, 32, and 64 QAM, all showing robust performance to noise and inter-symbol interference. When simulated with multipath fading, channel estimation was necessary to produce acceptable results. In general, we see that channel estimation methods trade off accuracy with computational complexity. We'll now go ahead and take a look at some of the MATLAB scripts used for simulation. This is the main OFDM simulation script. The first thing we do is input different parameters for the simulation. So here we're using QPSK as the modulation method, an FFT size of 64, a 16-length cyclic prefix extension. We are specifying a target SNR of 20 dB, telling the channel that it has 8 taps, and we're going to use least squares as the estimation method. This allows you to save the plots at the end to a specific file. So the first thing we do is we read in the image and translate it from three-dimensional array, where you have the XY dimension along with each RGB component, into a single binary stream. This binary stream is then mapped from bits 1 and 0 to symbols, which correspond to the modulation order. So for 8 PSK, the binary stream is grouped into blocks of 3, since 8 PSK is capable of summarizing 3 bits of information. Once this completes, we go ahead and modulate the signal based off of the specified modulation method. In this case, we're using quadrature phase shift keying. Now, the IFFT, inverse fast Fourier transform, is used to move the data to the time domain from the frequency domain, and a cyclic prefix extension is added. The data is then shifted from parallel to serial. Here we corrupt the signal with noise. The noise power is calculated based off of the target channel SNR value. The fading channel taps are calculated, and the time domain OFDM signal is convolved with the impulse response of the channel. Here, the cyclic prefix extension is removed, and the data is shifted from serial to parallel. The fast Fourier transform is then used to move the data from the time domain to the frequency domain. Here we apply channel estimation, in this case least squares. The data is then recovered from the modulated symbols and parsed back into a binary stream. That binary stream is then reshaped to form the image matrix. Once reshaped, the image is generated. And this last section of code generates all of the plots shown in the reports and presentation. From here, you have the option to save the image and rerun the entire script with either a different length channel, different type of channel estimation, a different SNR, or a different modulation scheme.